Okay, today's topic is bounded monotonic sequences. So first, a few definitions. So we say a sequence, a sub n, is increasing if the first term is less than or equal to the second term, and the second term is less than or equal to the third term, and so on and so forth. Remember, a sequence is a list of numbers, an ordered list of numbers. So a sequence is increasing if the numbers are getting bigger as you go down the list. Similarly, we say a sequence a sub n is decreasing if the numbers are getting smaller. So a1 is greater than or equal to a2, greater than or equal to a3. You will often hear this described as a monotonic property. So a sequence is monotonic if it's increasing or decreasing. So monotonic is this general idea where your sequence is either an increasing sequence or it's a decreasing sequence. We often will also define a strictly decreasing sequence if these are just strict inequalities. Similarly, we would say a strictly increasing sequence would have strict inequalities here. But generally, monotonic means your sequence is either increasing or it's decreasing. The next definition is for a sequence to be bounded. So basically, this means that your terms in the sequence are captured within a band. So you see here we have the sequence a sub n is bounded if there's some real number m such that all the a sub n's sit between minus m and big M. So if we draw that, you can think of, here's our n-axis. And then over here, on, say, the AN axis, this value would be M, and this value would be minus N. So we're saying that in this band, all of the terms of the a sub n live. So they could be jumping around, but they are always in that band. So this would be A1, A2, A3, A4, etc. So if this is true all the way down the line, that all these a sub n's sit below capital M and above negative capital M, then we say the sequence is bounded. So those are two key properties for sequences, and that leads us to this theorem, the bounded monotonic sequence theorem. And it says simply that every bounded monotonic sequence converges. So remember what it means for a sequence to converge. Intuitively, as you go down the list, the numbers are getting arbitrarily closer and closer to the limiting value. Let's think about what a bounded monotonic sequence looks like. So suppose, let's choose a sequence a sub n. Let's say it's an increasing sequence, and it's bounded. Then let's draw it. So the same kind of picture that we had on the previous page. Well, I should say the same sort of setup. That last picture was not monotonic, it was bounded. So here we have our bounded sequence. So we know, by the definition of being bounded, that all the terms in our sequence will lie in this band between minus m and m. But in this case, we're saying it's increasing. Remember, monotonic means increasing or decreasing, so we're saying let's just choose the case when it's increasing as an example. So suppose A1 is here. Well, A2 is either the same as A1 or bigger because it's increasing. So if it's bigger, let's say we're up here. Intuitively, the idea is because this is an increasing sequence, and we have to stay below this line of y equals m, sooner or later, the sequence has to choose some type of vertical asymptote in here. So suppose, for instance, that one possibility would be that from here on, from 2 on, every term in the sequence is just on this red line. In that case, the y value for the red line would be the limit of the sequence because all the terms would be equal to that number. Okay, well, suppose that they continue to go up after that. Okay, we can now make the same argument. Is this the limit of the sequence? Are all the terms sitting on that line thereafter? Okay, if the answer is yes, we're done. If the answer is no, we go higher. But as you can see, the idea is you can't continue this argument forever. Sooner or later, we're going to run up against this as a wall. So either this m is the limit of the sequence, or there's going to have to be some line in here that these points approach in an asymptotic way. And that's the intuition. That's the idea that any bounded monotonic sequence has to converge, has to have some kind of a limit. Okay, that's the idea. Now let's see it in action, and then let's look at this case of what we call a recursively defined sequence. So remember the way that a recursive sequence works. We are given some initial terms, and then we're given a formula for terms in terms of the previous terms in the sequence. So here, A1 is root 6. To get A2, we plug it into the formula. A2 equals root 6 plus A1, which is root 6 plus root 6. A3 is root 6 plus A2, and we saw here we can substitute this value of A2 in here. So this is root 6 plus, and that value of A2 was root 6 plus root 6. And you can keep going with this. So the question is, does this converge? And we can, in fact, argue that it does by exploiting this bounded monotonic sequence theorem. So, first, let's suppose we're plugging this into a calculator to try and get a sense for what's going on. So we use our calculator, and we see that the sequence starts like this. A1, root 6, is about 2.449. A2, here, this term, is about 2.907. The third term is about 2.984. The fourth term is about 2.997. And so when we look at that, it should be reasonable to guess, number one, that this sequence is increasing. We can see these numbers are going up. They're getting bigger. And it also looks like we might be bounded above by 3. We also can see that the numbers are greater than 0. So if we can make an argument that this sequence is bounded and it's increasing, then we can conclude from the theorem that it does in fact converge. So our first question is this bounded? Well, 1, we can see that a1, which is root 6, we know that's greater than 0. And then any a sub n, or any an plus 1, which is equal to root 6 plus a sub n, we can see if a sub n is greater than 0, then a sub n plus 1, which is root 6 plus that a sub n, is also greater than 0. And since a sub 1 is greater than 0, this combined with this fact is an argument by something called mathematical induction that tells us that all of our a sub n's are greater than 0. So that means we know that it's bounded below. How about bounded above? Well, remember we said this thing looked like it might be bounded above by 3. So suppose that a sub n, say for capital N, is less than or equal to 3. Well, we can then go back to the definition of the next term. A sub n plus 1 is root 6 plus that a sub n, but we just assume that that a sub n was less than or equal to 3. So this is less than or equal to root 6 plus 3, using the assumption that a sub n is smaller than 3. And of course, root 6 plus 3 is root 9, or 3. So this tells us if some n, if for some n, a sub n is less than or equal to 3, then all a n plus 1, a n plus 2, so on and so forth, are also less than or equal to 3. And the reason why it works for every term thereafter is this rule says if you find one that's less than or equal to 3, then the next one is less than or equal to 3. But then you can repeat that argument. Then the one after this is less than or equal to 3. So on and so forth. So if we can find one term in the sequence that's less than or equal to 3, then all the rest of the terms are less than or equal to 3. But look here, the first term is less than or equal to 3. So since a1 is approximately 2.5, which is less than 3, we found such an n. Specifically, n equals 1 did the trick. So this argument tells us that this sequence is bounded above by 3. Okay, so we have that a sub n is greater than or equal to 0 and less than or equal to 3 for all n. So our sequence is bounded. How about monotonic? Well, remember, looking at these numbers in the sequence, it looks like this is an increasing sequence. So let's actually confirm that. Well, we know by the definition that a sub n plus 1 is the square root of 6 plus a sub n. So we can tinker with this. Let's square both sides. an plus 1 squared is equal to 6 plus a sub n. Now we can do a trick where we subtract a sub n squared from both sides. If we do that, this becomes an plus 1 squared minus an squared equals 6 plus a sub n minus a sub n squared. And this right-hand side factors into 3 minus a sub n times 2 plus a sub n. Now remember what we argued before. We argued that every a sub n was less than or equal to 3 and bigger than or equal to 0. If a sub n is between 0 and 3, we are from 3 subtracting a number between 0 and 3, which means this term here is greater than or equal to 0. So again, that's because 0 is less than or equal to a sub n is less than or equal to 3 by our previous analysis. Here, this is also bigger than or equal to 0 because a sub n is positive, is non-negative. So we're adding to 2 something non-negative. That means that the product here is greater than or equal to 0. Okay, now connect the ends of this. So this and this here. So thus, a sub n plus 1 squared minus a sub n squared is greater than or equal to 0. A sub n plus 1 squared is greater than or equal to a sub n squared. And because our a sub n's are all positive, an plus 1 is greater than or equal to a sub n. Again, because the a sub n's are greater than or equal to 0. This is the definition of increasing. So thus, our sequence is increasing. So we've now confirmed that this is, in fact, a monotonic sequence. Now, bringing this all together, we have that our a sub n sequence is bounded and increasing, which means by our theorem that it converges. Now, since it does converge, for these types of recursively defined sequences, we can often find the limit. So what does it converge to? Well, let's go back to the defining equation. So remember, we had a sub n plus 1 equals the square root of 6 plus a sub n. And now let's take limits of both sides. So the limit, as n goes to infinity, of a sub n plus 1 equals the limit as n goes to infinity of root 6 plus a sub n. Now, because the square root of x is a continuous function, this limit can be brought inside the square root sign. So this becomes the square root of the limit as n goes to infinity of 6 plus an. And then the limit of the sum is the sum of the limits in this case, because both of the limits actually do exist. So this is the square root of 6 plus the limit as n goes to infinity of a sub n. So we look at that and think, okay, did we really accomplish anything? And the answer is yes, we did. And again, let's look at the expression on the left and the expression on the right. So we can rewrite that. We have the limit as n goes to infinity of a sub n plus 1 equals root 6 plus the limit as n goes to infinity of a sub n. Now remember, our bounded monotonic theorem tells us that this limit and this limit both exist. The a sub n sequence converges. And the key insight here is to recognize that this limit and this limit are the same. And you can think of it in the following way. Suppose we picture our number line. And so we have some general expression. Right. Here's a sub n. Well, this sequence converging means that there is some limit let's say that this is our limit L. So in general, these a sub n's are approaching that limit, this limit of L. Well, an plus 1 is right here. So if these an's are on their way to L, then the term that's one step in front of them are also going to L. You can think of it like both of these two terms are people on a roller coaster. And the roller coaster car. And the roller coaster car is going to this limit L, which means the passengers are both going to that same limit L. That's an argument that this limit and this limit are in fact the same. So this is the nth term, and this is just the term that's one step ahead of that nth term. So what we do is now just rename these L. And we can take this expression and say L equals the square root of 6 plus L and solve for L. So L equals the square root of 6 plus L. Square both sides. L squared equals 6 plus L. L squared minus L minus 6 equals 0, which will factor as what? L minus 3 times L plus 2. So this equation is solved by L equals 3 and L equals minus 2. Now we know that this can't be the limit because all the an's are greater than or equal to 0. So this must be our limit. And that's what L was. L was the limit. So L was the limit as n goes to infinity of a sub n. And we've just concluded that it's equal to 3. So in these cases where you have a bounded monotonic sequence with a recursively defined sequence, you can use this approach to calculate the limit.